Three problems are related. In part A, determine if the series, this is an alternating series because we got negative 1 raised to n. We need to show if this series is convergent or divergent. In part B, determine if the series is convergent or divergent. It's the same series like part A without negative 1 to the n. It looks like if we take absolute value of inside, when we take absolute value, this negative 1 to the n will be just always positive. So we have that situation. And in part C, it asks, using part A and B, conclude if the series, with this alternating series, is absolutely convergent, conditionally convergent, or divergent. So let's answer part A. So obviously this is an alternating series. So whenever we have an alternating series, we want to use the alternating series test to show if this series is convergent. And unfortunately, the alternating series test can't conclude anything about divergence. But let's try for AST, alternating series test. We are doing part A. And for the alternating series test, negative 1 to the n and some other terms, positive terms, that we denote by Bn. If we are able to show these Bn's are decreasing and the limit of Bn when n goes to infinity is 0, then this series converges. So let's see Bn. If Bn's are decreasing, if that is the case, all I am trying to write here, if Bn's are decreasing, we're asking, maybe let me put Bn. The Bn's are 1 over cube root of n, So when n goes bigger and bigger, cube root of n is also bigger. When the bottom is bigger, 1 over bigger number means smaller. Yes, when n gets bigger and bigger, these terms are getting smaller and smaller. So this is true. Or we can say Bn's are decreasing. We can just write Bn's are decreasing. In second part for the alternating series test, we need to show if the limit of Bn when n goes to infinity is 0. So limit as n goes to infinity of Bn is 1 over cube root of n. So n is really big, cube root of really big is also big, and 1 over really big is very small, that is 0. Yes. So from 1 and 2, let me put not A and B, maybe 2 parts of the alternating series test, we showed both true. So by the alternating series test, the series converges, or the series is convergent. That part A. Now part B, it's about the same like this one, but without negative 1 to the n. So the series is, let me rewrite, no need to rewrite, but I'm just kind of wasting some time. This is the series. And if we look at closely, this is cube root of n. That is pretty much like n raised to 1/3. So this is a p series, right? This one I can rewrite in this way: 1 over n raised to 1/3. This is a p series with p equals 1/3. And we know that when there is a p series with p less than or equal to 1, the series diverges. which is, we can write less than or equal to 1. In fact, strictly less than 1. Even this is 1, the series diverges. Less than 1 implies the series diverges. Okay, so part B, divergent, part A, convergent. Then we can now just conclude about this series. I mean, this one is with absolute value. Without absolute value, convergent. With absolute value of this one, it's divergent. And that is exactly conditionally convergent case. Okay, so from part A and B, we can say the series, this series is conditionally convergent. If both converges, that would have been absolutely convergent. Okay, if both divergent, that would be divergent. Final.